Okay, exponential functions. So we're going to look at some key features for exponential functions. In general, the equation is y equals ab raised to the x power. And a is going to represent the initial amount, and b is going to represent how fast it's either growing or decaying. And then x is usually time, or it could be the number of increments. So let's look at this for example. While studying her family's history, Angie discovered records of ancestors 12 generations back. She wondered how many ancestors she had in the past 12 generations. She made a tree, but the diagram soon became very complex. So here's her diagram down here. So Angie came from 2 parents, and each one of those parents came from 2 parents, and each one of those came from 2 more. And we would just keep going. So this would be like generation 0. This would be generation 1, 2 generations back, 3 and so on. So we look at the table. At generation 0, we just have Angie. And then the first generation, there's 2. The second generation, there are 1, 2, 3, 4 people. The third generation, 1, 2, 3, 4, 5, 6, 7, 8. And so what you notice is, hopefully, is that as the generations go up by 1, to go from one number to the next is a multiplication. So if we multiply 1 times 2, then 2 times 2, we get 4. 4 times 2, we get 8. So the next generation, if we multiplied by 2, would have 16 folks in it. And the 5th generation would have 32 people in it. So if we wanted to write an equation using our y equals ab to the x, y would equal the initial amount. So we're looking at 1. And how fast? Well, it's going up by multiplications of 2. For these in the table, it's how much is it being multiplied by. And it's growing, raised to however many generations. All right, it's March Madness, and the basketball tournament starts with 64 teams, let's say. And each round, the losing teams are eliminated. So if we start with round 0, we start out the tournament with 64 teams. So after they play their first game, half of those teams would be eliminated, because there's only going to be 1 team that moves on. So this would get cut in half, so 32. And then round 2, now there would be 16 teams. And then third round, we would have the Elite 8. And then the final 4. Until we get all the way down to the winning team. So when you look at our table this time, as the rounds go up by 1, these are decreasing. And so if we had to multiply 64 times something to get to 32, we would multiply by 1/2. Yes, it is being divided by 2, which is the same as multiplication by 1/2 each time. So if we want to write an equation for this, we could say y equals our starting amount, so 64, times how fast it's increasing or decreasing. Well, it's decreasing this time by 1/2 for each round. So notice that it's a decay. All right. So if we go back, when it's increasing, the b value, the number in the parentheses, is larger than 1. When it's decreasing, as in the basketball case, then b, or the amount, or how fast, is a fraction. So this leads us to our essential understanding. Y equals ab to the x, where b is the positive number other than 1. So for this function, if a is larger than 0, and b is larger than 1, b is bigger than 1, then we have something that's growing. if b is anywhere between 0 and 1, in other words, a fraction, then we would have an exponential decay. It will be decreasing. In either case, the y-intercept, 0, a, the domain, is all real numbers. Okay, and we would have what's called an asymptote. We're going to look at some graphs here in just a few minutes. If we're talking about something that's a rate, like, for instance, money, like if you put money in a bank and it's going to grow at a 3% interest rate, then you could use this formula, okay? And we'll look at that in some examples as well, okay? So the graph of y equals 2 to the x, if you make a table of values, so we're going to put in -4 into the x value, and that, if you put that in your calculator, you get 1/16. Put -3 in, 1/8, or 0.125. So we're using our calculators to do that. And so when you look at your graph on your table, 2 to the 0 is 1, 2 to the first is 2, 2 to the second would be 4, 2 to the third is 8. And so when we plot all these points, you can see the generalization of the graph. Kind of looks like a J type shape. And the word asymptote means that this graph is not going to be able to get smaller than this x-axis. It won't dip below. In general, our asymptote would be at the x-axis when y equals 0. Okay, you try to graph this one. Y equals 4 raised to the x power, and pause the video. Okay, check your answer. So if you put 0 in, 4 to the 0 power is 1. 4 to the first, when x is 1, you get 4. If you were to put negative numbers in there, so if you put -1 in for x, you get 1/4, etc.
Identify exponential growth and decay. Identify each function or situation as an example of exponential growth or decay. What is the y-intercept? Remember that for the function y equals a times b to the x power, if a is greater than 0 and b is greater than 1, the function represents exponential growth. If a is greater than 0 and b is greater than 0 and less than 1, the function represents exponential decay. $9,500 is between 0 and 1. Since the value of b is between 0 and 1, the function represents exponential decay. For the function y equals a times b to the x power, the y-intercept is 0a. The y-intercept for this function is the value of a, which is 12. Part B is the function y equals 2,500 times 2 to the x power, an example of exponential growth or decay. What is the y-intercept? Is greater than 1. Since the value b is greater than 1, the function represents exponential growth. The y-intercept is the value of a, which is 2,500. Part C. You put $1,000 into a college savings account for 4 years. The account pays 5% interest annually. Is this situation an example of exponential growth or decay? What is the y-intercept?
Okay, so for this one, since we're dealing with money and we have a rate, we're going to use that other formula, the y equals
The
So what do you start with?
What quantity does the y-intercept in this situation represent?
It's your initial amount of money.
The y-intercept is the amount of money at t equals 0, which is the initial investment. The y-intercept is 1,000, which is the dollar value of the initial investment. Now it's your turn. Step 1. Determine if an exponential function is a reasonable model. The money grows at a fixed rate of 5% per year, so an exponential model is appropriate. Step 2. Define the variables and determine the model. Let t equal the number of years since the money was invested. The growth factor b in an exponential function can be expressed as the initial amount 1 plus the percentage increase r. A reasonable model to use is a of t equals a times the quantity 1 plus r raised to the t power.
Okay, so let's look at that one together. So we're going to use this formula. So A is going to equal, what did we start with? We were starting with $1,000. And then 1 plus our rate. Our rate is 5%. We're going to write 5% as 0.05. 5% means 5 divided by 100. So if you had to put that in your calculator, you get 0.05. Raised to the t, which is the number of years that we're going to leave the money in the account. So we're looking at 6 years. So we're going to put that in our calculator. So we put it in our calculator here. I just did 1 plus 0.05 on my own. Typed it in. And so at 6 years, we would be looking at $1,340 and about 10 cents. Alright, suppose you invest $1,000 in a savings account that pays 5% annual interest. If you make no additional deposits or withdrawals, how many years will it take the account to go to at least $15,000? So for this one, I'm going to use that same formula. A there. My initial amount. So this time we want this to be $1,500 at the end. We're going to start with $1,000 and 1.05, and we want to try to figure out t. So what we can do is use our calculators and look at our table to see how fast we could get to $1,500. Okay? So here we have our equation that I wrote previously. You're going to put this in your calculator and you're going to go to table and make a table using the table feature on your graphing calculator. Find when the input is $1,500. So we're going to scroll through there until we find out that it happens at about 9 years. The 9th year. Or I'm sorry, after the 8th year is the 1,500. For an exponential function, the table shows the world population of Iran from 2003 to 2004. If this trend continues and the population is decreasing exponentially, how many will there be in 2014? Okay, so we need to figure out how fast is that happening. So remember the exponential is about how much we're multiplying by. Are we multiplying by 2, by 3, or are we multiplying by a fraction 1/2 or 1/3? And since it says that it's decreasing, we should be multiplying by a fraction. So we have to determine r. So to do that, we're going to subtract out of the, and then